Welcome to the 2023 Physics Slam. I'm Kai Fu. I'm a professor with a position joint in physics and electrical computer engineering. I am really excited to just kick off this event. I'm going to keep my comments brief because this is run by the students and I will let them take over the show, but I do want to say a couple of things. This will be a super fun event. You'll find out why and how it works in a few minutes. This is a very special slam because it's held in conjunction with the Conference for Undergraduate Women in Physics. You can look around you right now and may realize that this may not be the typical audience that you would expect to see at a physics lecture at 8 p.m. on a Saturday night. And that's because the University of Washington is hosting CUWiP, Conference for Undergraduate Women in Physics, this year, and has welcomed over 140 women who are undergraduates in physics. And this has been a very exciting weekend. So the Conference for Undergraduate Women in Physics and also the SLAM, there's many people to thank for this event. From individual donors to also corporate donors, and I would like to do a special call out to Amazon, who provided $10,000 of support for the conference this year. I would love to thank everyone who makes broadening participation in physics a part of their lives, and that includes all of you for being here. Many of you donated just to have a seat here, so that's an amazing start. And keep doing that. Keep building the community of what we want to see the face of physics to look like in years to come. If you want to do even more, this always is at our events. You always are welcome to donate on the Conference for Undergraduate Women in Physics website. Come to more events by the SLAM, more slams. We have them every year. We also have Frontiers in Physics lecture series. Why am I mentioning this? Because I'm super excited to announce that our next speaker in May, so May 17th, mark your calendars, is Kip Thorne. You guys heard it first. Who will be speaking. His title of his talk is My Romance with the Warp Side of the Universe, from Black Holes and Wormholes to Time Travel and Gravitational Waves. That said, I still would not be surprised if tonight's going to be more fun. So, with no further ado, I'm going to hand this off to today's MC, Shi Wang, who is a graduate student in the physics department. Oh, postdoc. Postdoc in the physics department. All right, let's welcome Shi.
Okay, ladies and gentlemen, welcome to Physics Slam 2023. After this long COVID lockdown, we finally have the opportunity to gather here to enjoy the physics tonight. We have five wonderful speakers from 5 different fields of physics. Every speaker will give us about a 10-minute presentation introducing their research. And we will have a Q&A session at the end. You can ask any questions that you want. And also, we are going to have a voting at the same time. So please vote for your favorite talk tonight. And we prepared awards for our speakers with the favorite talks and souvenirs for all of our speakers. So let me put this out. So our first speaker is Dr. Dyson Water. Dr. Dyson Water is an ORISE Intelligence Community Postdoc Fellow in the Physics Department. He's my colleague at the University of Washington. Dyson is going to share with us his cool research on 2D materials and the superlattices. And our second speaker is Professor Sarah Meridian. So Professor Sarah Meridian is an assistant professor in Electric and Computer Engineering Department at the University of Washington. Sarah's research focuses on building quantum technologies out of trapped ions. And let me flip. And our third speaker is Dr. Sarah Greenstreet. Dr. Sarah Greenstreet is a research scientist at the Data Intensive Research in Astrophysics and Cosmology Institute in the Astronomy Department at the University of Washington, Seattle. And she's going to tell us wonderful stories about astrophysics. So, our fourth speaker is Professor Masha Bayakta. I apologize for that. I practiced. I promise. Professor Masha Bayakta. She is an assistant professor in physics department at University of Washington. Masha is a particle theorist interested in predicting and searching for new physics beyond what we have discovered so far. And our last speaker is Professor Alana Perlik. Professor Alana Perlik is an assistant teaching professor of physics at University of Washington, Bothell. Her research is in physics education, specifically focusing on how students, faculty, and teaching assistants engage with collaborative learning environments in introductory physics. So I just introduced all our speakers. And now let me shift the spotlight to Dr. Jason Water.
Sorry about that. Okay, I think everyone can hear me. Yeah, good, awesome. All right, great. So yeah, my name is Jason Waters. I'm a postdoc here at the University of Washington. I'm an experimental physicist, and I work on a set of quantum materials. I know everyone's eager to break out these 3D glasses, but I'm going to stick to 2 dimensions. I work on 2-dimensional materials, and I want to talk to you tonight about some of the cool things that we can do with these materials, stacking, twisting, and a bit of magic that's going to come along for the ride. Technical difficulties already, great. Okay, there we go. All right, so what do I mean by quantum material? We're going to be talking about quantum mechanics, the physics of the very small, right? So atoms, electrons, how they move and interact with one another, right? And then whenever I say materials, I mean something very specific. I mean a crystalline arrangement of these, a periodic arrangement of these atoms, okay? So this is a crystal structure, and we're going to be talking about the electronic properties of these materials, how electrons move through these materials, and what properties they might have, all right? And whether or not you're aware of it, you're probably quite actually familiar with a quantum material. This is a picture of one of the first silicon transistors that was invented back in the 1950s. And it is a semiconductor. It's a quantum material where sometimes electricity can flow and sometimes it doesn't. That state of whether electrons flow or not in that material can be translated in binary, 1s and 0s. We can do operations with these. We can make them really small and cram a few billion of them into the processor on your phone, and you get all the marvels of the modern technological revolution that we're in, right? So next time you're scrolling TikTok on your phone, you can thank quantum mechanics for that. And I'll let you decide if that's a good or a bad thing. So that's where we've been with quantum materials. We can do a lot with them. They're very powerful, but I want to talk about where we're going next. And so my work focuses on what are the cool things that we can do with these materials, okay? And so I want to convey, you're going to learn a lot of cool physics tonight. You're going to see a lot of cool images. I want to convey 2 ideas. We're going to keep it really simple. The first idea, if you only take two things away from this talk, this is one of them, is that structure determines properties. Okay, that's my first big idea. So let's walk through an example of what I mean by this. All right, so let's take diamond, a material that everyone's familiar with, right? Very, it's transparent, it's very tough, strongest material in the world. It's electrically insulating, and I want to compare that to the case of graphite, the stuff that's in your pencil lead. In some sense, I can't think of a more opposite material. It's opaque, it's very brittle, it's electrically conducting. Please don't go like putting your pencil up to a battery, just trust me, it's electrically conducting. You might ask, why am I comparing these two materials? They're so different. Well, they're made from the same atoms. They're made of carbon atoms, right? They're just arranged slightly differently. So this is the atomic structure of diamond. It's this like complicated looking cubic lattice. This is the atomic structure of graphite. It comes in these layered hexagonal sheets, right? And you can already see why graphite's a good writing utensil, right? The layers come off as you drag it across the page. So just taking these same atoms and rearranging them slightly differently gives you vastly different properties, right? That's what I mean by structure drives properties, okay? Obviously it means what is it made of, but also how is it arranged. And this is a particularly relevant example because some physicists back in 2004 looked at the structure of graphite and were like, oh, hey, like what if we could isolate this to just a few atoms thick? And they were actually able to go a step further and isolate it to a single atomic limit. And this is called graphene. It's the first ever two-dimensional material. There was a Nobel Prize awarded for this. It's two-dimensional in this sense that if I put an electron in here, it's confined to the plane of the graphene, right? There's only x and y. There's no z direction, right? You might be asking, like, what is this remarkable, like, scientific technique? This must be $1 million instrument to isolate a single layer of graphene. Some of you already know the butt of the joke. It's not. It's just Scotch tape. We just take some Scotch tape, we put graphite on a piece of tape, and you just cleave it a few times. You put it on a substrate, and you're bound to get some graphene, right? Here's a picture of what that kind of looks like. So a really accessible technique. And it's really cool. Graphene's a metal. It's a very special metal. It's interesting in its own right. But why I bring it up is that it really sparked a revolution because we realized we have all these different layered materials. And they have different properties. We can do semiconductors that are two-dimensional. We can do insulators or magnets. Whatever you want, we have it as a two-dimensional material. And owing to that two-dimensional material, I can start taking them one layer at a time, one by one, picking them up and stacking them together, like so, just a little schematic of this. And whenever I create this like final composite object, for this example, I don't care what the individual layers are, but the composite object is going to have vastly different properties than any of the single layers by themselves, right? Because we know that structure determines properties. So this is actually what I do in the lab all day. I get to play, we all often make the analogy that I'm playing with Legos. I'm just taking all these materials, I'm combining them in new and different ways to come up with some engineering application or some new physics that I want to see. Okay? So 2D materials are really cool. We can combine them in a lot of interesting ways, and we actually have a kind of a novel tuning knob. So here I'm showing two sheets of graphene, my hexagonal graphene lattice. They're right on top of each other, so you can't distinguish them now. But I'm going to hold one of them fixed. I'm going to start rotating the other, and something quite remarkable happens. Let's see if we can see it well in this lighting. Can we see this like larger scale periodic pattern emerging? Yeah, so this is called a Moiré pattern. It depends on I don't know, you can look at it with the 3D glasses. This was not planned, I don't know. Oh gosh, now I want to. All right, anyways. So this Moiré pattern, this interference pattern, it depends on the twist angle, right? That it grows and shrinks depending on the angle. If I freeze it here on 1, you can just see that like larger wavelength pattern. You might think that this is some cute trick that I'm playing, right? It's some kind of optical illusion. But remember, in these materials, structure drives properties. Structure determines properties. So this is going to radically change what happens to the electrons in that system. Just to give you an idea what it looks like, this is an image of a flake of graphene that I exfoliated the other day. The color contrast shows like different numbers of layers. So like, does my laser want to work? 1 layer, 2 layer, 3 layers of graphene, right? There's a scale bar here, 20 micrometers, but just for reference, this is a microscope image to scale of a typical human hair. So we're talking very small, but we can reliably pick these up, stack them together, and fashion little devices out of them. So these gold wires are like leads, and I can start poking and prodding this material to see what cool stuff happens to it. Okay? So to talk about what cool stuff can happen, I want to introduce my second point, right? So this is the second idea if you only remember 2 things. So this is the second one. When electrons start to interact, cool things start happening, all right? So what do I mean by that? Well, there's lots of ways this can come to play, but let's just imagine I have a, this is a cartoon picture of my crystal lattice here, and I ask what happens when an electron goes into the system. If I try and pass a current through this, and this is just some normal material, the electron's going to go through and it's going to bounce off of all these ions in the crystal lattice, and it's going to give off waste energy in the form of heat and light. That might be great. You might want a light bulb, you might want a heater, but if you're trying to do low power electronic devices, or if you're trying to transmit a bunch of energy over long distances, this waste energy can be problematic, right? So one cool thing you can do is you can realize that this picture, I'm only considering one electron, and I can accurately describe the physics as it bounces off these atoms, just considering that single electron. It doesn't care about all the other electrons that are around it. We'll often call this a single particle picture, the single electron picture of this material. But if you start letting the electrons interact with one another, some really interesting things can start happening. So, you have your single electron, it's been sitting on the couch. Maybe it's been a long pandemic, it's watched way too much Netflix. What are any of us in that situation going to do, right? We can turn to online dating, right? So this electron can go on to its favorite. I'll be here all week, yeah. This electron can go into its favorite dating app of choice, Spender or CUWiP. Okay, that's it. I'm done. All right, so it can go into its favorite online dating app, and it's like, okay, it needs to make a profile, right? So it's a spin-up electron. It's moving to the left. It's got some momentum left. It needs to find an appropriate match. And for this example, it finds an electron that's spin down, momentum to the right. And if the conditions are just right, it can pair up. Okay, so these electrons start interacting. They start pairing up. There are other ways to pair up, if you know what I mean, but this is good enough for now. This is called a Cooper pair. And a Cooper pair does something quite remarkable. When it passes through a material, it does so with absolutely no energy loss. No energy loss whatsoever. When I mean no energy, I mean none. It's perfect. Nothing's ever perfect in physics. So superconductors, which is what this is called, superconductivity, they're quite cool. They're one of the more exotic phases of matter that we can create in the lab. You might know where I'm going with this. So we have these electrons in graphene. Ordinarily, single particle picture is good enough. Then we start using this tuning knob of twist angle, and when we approach something called the magic angle, it's about 1.1 degrees, these electrons start pairing up, and graphene becomes a superconductor. Okay, so let's not get lost where we started. We started with just pencil lead, right? And we use these key ideas that structure determines properties, and that electrons interacting, we can get some cool things happening, and we create superconductors. Okay? So with that, I'm going to wrap up. Remember my two big ideas: structure determines properties. With 2D materials, we can combine all of these different materials in new and interesting ways. And when electrons start interacting, cool things start happening. And we're only just scratching the surface of what 2D materials can do. So with that, thanks for your attention.
Hey. Oh no, you didn't do it? Okay, perfect. Let's not do that. Okay. All right, hello everybody. My name is Sarah Meridian. I am a professor in electrical and computer engineering. I do a lot of applied physics, and I try to build things out using our physics knowledge. And what I'd like to tell you about today is how and why we can tame the quantum world. So as we just heard, quantum mechanics describes what happens on the atomic scale. So it describes what happens when atoms interact with other atoms, electrons interact with other electrons, atoms interact with light fields or electric fields. And in some ways, as we heard, quantum mechanics describes everything around us. It tells us why graphene behaves the way it does. It tells us why glass is transparent. But we are classical beings, and in general, we only see these collective effects. We're not able to understand what happens at the individual atomic scale. But in the last decades, there have been a lot of technological improvements that have allowed us to be able to probe what happens atom by atom, control their state, and measure their state as well. So quantum mechanics was postulated and developed in the 1920s, and then by the 1960s we knew enough to build technologies that use quantum mechanics. So on the left here we see an image of a brain slice taken by a magnetic resonant image, or an MRI. And here we're using the fact that if you have a really, really large magnetic field, the spins in hydrogen start processing. And we can measure that, and knowing, with our understanding of quantum mechanics, we can know how to take that signal and get biologically relevant signals from it. So for instance, the density of material, if you have a lesion in your brain, or if you've snapped a tendon in your knee and can't go skiing next weekend. We also have lasers that use the fact that certain materials, when you apply an electric field or some large source of energy to them, create light at very particular frequencies, at very high powers. Okay, but these technologies were not changing the quantum properties of the materials. We're just using our knowledge of quantum mechanics to build something useful. So the classical example I'd like to tie it to is wind turbines, right? In a wind turbine, we're not controlling the wind, but we're using the wind. We're using our knowledge of how wind works and how wind moves things to create energy. Okay, but what we'd really like to do is go beyond that, right, and actually make engineered quantum systems. And so the question is why? I mean, first of all, it's cool, right? It's nice to be able to do new things. But it turns out we can do a lot of useful things with engineered quantum systems. So first, the most naive thing we can think about is using a engineered quantum system, one that we can control, to simulate something of use. So what I have up here is nitrogenase. Nitrogenase helps us turn energy in soil into something that we can eat. And if we could understand exactly how it works, which we don't totally know yet, but if we could understand how it works, and then we could change it or find a way to make it more efficiently, we could create food more efficiently and then solve world hunger and do other amazing things. And it turns out that, so using an engineered quantum system can actually help us do that. Okay, the other thing is we can think of quantum information just as we think of classical information. So in our computers, we take some classical information, we do some operations on it with transistors, and then the output encodes the answer to something that we're interested in. Turns out you can do the same with quantum information, take a bunch of encode information in a quantum system, do a bunch of quantum operations, and get an answer out of it. And for some particular problems, that gives you improvements that are faster than anything you could do on a classical computer. We can also improve navigation. So the GPS in your phone actually already has to use atomic clouds to figure out where you are. So the fact that these atoms have very particular frequencies allows them to measure time really well, which then allows them to measure position really well. But you could get even better, more accurate GPS if we could control these atom systems even better. And the last thing is that if you have two quantum systems, you can share secrets between them and prove that no one is listening in on your secrets. Okay, that's a very quick motivation for why we want to control quantum systems. So now I'd like to talk about how we control quantum systems. So we work with single trapped atoms, but to trap a quantum bit and extricate it from all of the other atoms in your system, you have to make it interact with something that you can control. There's many ways to do this, but what we do is we rip off an electron. And so we make this charged atom, we turn it into a positively charged atom or a positively charged ion. And charged particles are nice because they interact with electric fields. So then all we have to do is shape our electric field. And we're fairly good at doing that. We know how to make electrodes that create different electric fields. We have DC voltages and AC voltages, but we need to shape this electric field into something that can confine our electron. So and you can think of electric potentials and how ions interact with electric potentials in the same way that balls interact with gravitational potentials. right? So if I had a hill like this or a potential that's decreasing linearly, the atom is just going to fall off and be lost. So what we want is some sort of confining potential, like the potential here, so that the atom will be stuck in the local minimum. And what we want to do is we want this in 2 dimensions and eventually 3 dimensions. However, there's a problem. The problem is that it is prohibited by the laws of physics to have a fully trapping potential. There is no way that you can create, or anyone can create, an electric field that traps a charged particle in all 3 dimensions. That's a problem. But we can play a trick. And the trick that we play is we have a moving electric field. So here this is a freeze frame of a 2D electric field. And this is our little ion. And you can see here it would just fall down right here, right, at this freeze frame. But now we switch the electric field back and forth. And as long as we're switching the electric field, the polarity of the saddle back and forth fast enough, faster than the ion is moving, every time the ion tries to escape, it's going to be stuck back, right? And in this way, we can keep the ion, even though we can't at any instantaneous moment keep it trapped, we can keep it trapped on average. And we know how to create alternating electric fields. We use alternating voltages, or DC or AC voltages, or RF fields. Okay, so now that we know how to trap atoms, a single ion, we want to trap lots of ions, and so this is actually a schematic of a trap that we use in my lab, and also another physics professor, Professor Blinov at University of Washington, uses in his lab. And actually the technology behind this trap was developed by Professor DeMelt, who later came to University of Washington. So the history of ion trapping is deep within University of Washington. So these are 4 RF electrodes and 2 DC electrodes, and if we put the voltages correctly, we can create this linear chain of ions, and then we can take pictures of them. So these are actual pictures of 2 ions, 3 ions, or a bunch of ions. And we have them all in a line, and then we can shoot lasers at them, control them, look at their fluorescence to measure their state, and eventually profit. And then the most important thing that we can do is have fun and start doing experiments. So this is a trap where instead of trapping a line of ions, we have a circularly symmetric trap, and we can control the voltages on these electrodes here. So these are all DC electrodes, and allows us to create nice videos of ions move. So this is a real-time video of 2 ions rotating around each other at 1 time a second. And that's just by changing the voltages around these electrodes. And there's a lot more that we can do with these systems, but with that, I'll leave you with excitement about what we can do with quantum mechanics.
If anyone doesn't have their glasses, they probably should grab some glasses. Yeah, that's a good time.
I always go faster when I'm when I'm in person.
That's good because I think I'm like bored now. I think it's easy to see with me too.
Yeah. I knew it. I was like,
Okay. All right. Well, hello, everyone. My name is Sarah Greenstreet. I am a research scientist here in the department, or in the astronomy department, here at the University of Washington. I'm going to change our scale here a little bit. We're no longer talking about the quantum scale, but we're going to go out to the scale of the solar system. So I have had the very great privilege of getting to work very closely with the science team for NASA's New Horizons mission to Pluto. So tonight I want to share with you some of the spectacular images of Pluto that came out of that mission, as well as tell you what I think is the most exciting discovery that came out about Pluto from that mission as well. So first I want to start to give you a little bit of context. I want to show you this picture. This is the best picture that we had of Pluto in early 2015 before New Horizons made it to Pluto. This was taken with the Hubble Space Telescope, which we know takes spectacular images, but Pluto is pretty far away. It's small, it's faint. This is the best that we could do. And so it took us actually being able to send a spacecraft there to get any more detail of this. But believe it or not, there was a lot of science and geology that was done with this picture for many years. So the first gift that New Horizons gave us, as soon as it did its flyby and started sending pictures back to us, was to turn this picture of Pluto into this picture of Pluto. And I still get chills every time I see that transition, because the level of detail in these pictures and the amount of science we can do is just mind-blowing. So one of the first things that we noticed when these pictures started coming back is this very prominent heart-shaped feature on the face of Pluto. So this heart is going to be really important for my talk here. So at this point, I want to start showing you some of those pictures. We're going to zoom in here onto the surface of Pluto, and we're going to kind of move around this heart-shaped feature in kind of a C-shaped pattern around the outside edge. So I'm really excited as well, because this is where you get to use these 3D glasses. So now is the time to put those on. Make sure that you have red on the left. That is important for making sure that things pop out at you the right way. So red goes on the left. Okay, so here we go. So we're gonna go through these kind of quick, since I only have 10 minutes. So you'll notice on the top left of all of these slides, I've got a little picture showing which part of the face of Pluto we're actually looking at here. So this is the eastern side of that heart-shaped feature. And you'll notice that there's quite an elevation difference between these two parts of this picture. On the right-hand side, the highlands are about a mile higher in elevation than the plains on the left. And these giant chasms that you see on the right-hand side, these are large enough, to give you some context, to be able to hide Mount Rainier in any one of them. So these are giant chasms on Pluto. And these little tiny specks on the left that kind of look like ants marching around on the surface, these are giant pits in the ice. Every single one of them is at least several football fields in size, to give you an idea of the scale that we're talking about here. Okay, so moving on, this is now moving northeast of that heart-shaped feature. And this is called the bladed or snakeskin terrain on Pluto, because of this kind of ridge-like wrinkly pattern that it has. This covers a huge part of Pluto's surface. This is about 250 miles across in this image alone. And this is unlike anything we've seen anywhere in the solar system. We don't actually know what causes this type of terrain, but it's definitely something that we're trying to figure out. Okay, so moving on, we're now zooming out a little bit. So this is kind of cutting across the north part of that heart-shaped feature. So the eastern side is on the top right and down the right-hand side. The lower left has the northwest part of that heart, and on the top left is kind of the highland area that's in the top, in the divot of that heart here. And you can see again that there's a really extreme elevation difference, in particular between the highlands here in the top left and the plain on the bottom left. And here you can see we're moving westward now. You can really see this difference. So there's about 1.5 to 2 mile elevation difference between these very rugged highlands, where you can see a lot of different geological features here, and this very smooth, flat plain down below that makes up the western side of Pluto's heart feature. So this isn't a 3D image, but you can keep your glasses on, because I've got a couple more here. I want to take a second to talk about this very smooth part of Pluto's surface. It makes up the entire western half of this heart-shaped feature. And this is a nitrogen ice field that's present on Pluto. Now, the cool thing about nitrogen ice is that at the temperature present on Pluto, this has the consistency of something very similar to really thick toothpaste. So this is a frozen lake of nitrogen ice that's kind of like sticky toothpaste. So it's not quite a solid, but it's still ice. You'll also notice that there are these, I don't know if I can use this pointer, here we go. There's these big angular block mountain type of things down here at the bottom on the edge of this nitrogen ice lake. These are chunks of water ice, and water ice is less dense than nitrogen ice. So these are actually water icebergs floating on the edge of this nitrogen ice field, this frozen lake. So you can see there's some more of these down here in the bottom right-hand corner. Again, for scale, each of these is about the size of Mount Rainier as well. So these are giant water icebergs floating on the edge of this ice field, and you can see there's a bunch of these as well that have kind of floated to the edge of this frozen lake, much like you see when you go up to a lake shore and you see a bunch of sticks and debris that kind of get stuck on the edge. That's the same type of thing that we think is happening here. Okay, so this is my last 3D picture for you. I'm sorry I don't have more, but this is moving to the southwestern part of the highlands on Pluto. And one of the things you immediately notice are these giant lines that run along the left-hand side. These are fractures or cracks in the ice on Pluto. Each of these runs anywhere from 300 to 500 miles long, and they're several miles deep. So they're these massive fractures in the ice on Pluto. And another thing that you notice, completely covering this terrain, are these little circular features that are all over the highlands. So I want to take some time now to talk about these circular features. So you can take off your glasses because I don't have any more 3D pictures, even though I know it's fun to look at these. So these circular features are craters that are made by impacts from asteroids that hit the surface with enough energy that they leave a big hole in the ground. And the cool thing about these craters is that they allow us to be able to look at a chronological record of the surfaces of any solid planetary body within the solar system. They're all covered in craters. So we can do this by comparing different types of cratered surfaces that have different numbers of craters on them. Because these asteroid impacts happen at a relatively steady rate, we know that surfaces that have fewer craters are younger, and surfaces that have lots of craters are older because it takes longer to collect more craters than it does fewer craters. So we can apply this same type of chronology technique to the surface of Pluto to see if there's anything interesting that comes out of this. So to talk about this, we're going to divide Pluto into 3 sections. We're going to talk separately about the western side of the heart from the eastern side of the heart, and then we're going to talk about the highlands, everything around the heart-shaped feature. So let's take this last one first. From those pictures I just showed, these highland areas on Pluto's surface are completely covered in craters. So we know that this part of Pluto's surface is very old, and we can actually calculate that it takes the full 4.5 billion year lifetime of Pluto to collect this many craters on this part of Pluto's surface. Now things start to get interesting when we talk about the heart, because if you take the eastern side of Pluto's heart, there are some craters here, but not as many as around the rest of the heart-shaped feature in the highlands. So we know that this part of Pluto's surface is pretty old, but it's not very old. And it gets even more interesting when we talk about the western side of the heart. There is not a single impact crater seen on this part of Pluto's surface down to the resolution limit of the instruments on board the New Horizons spacecraft, which is incredible and not at all expected. So what is going on here? How come there are no craters here? Where did they go? And so let's take a little look here. These patterns here on the nitrogen ice field here, you can see them zoomed in here. I'm going to speed up really quickly. So we notice that this looks a lot like what the surface of water looks like when it's boiling. These little convective cells. And so we've figured out that this nitrogen ice toothpaste-like lake on Pluto is in fact boiling, but it's boiling very slowly because this is ice and it's thick toothpaste, so the process is much slower than when you boil water on your stove. So even more exciting, this means that this is erasing these craters, which is something that is still happening today, which means that Pluto, this 4.5 billion year old small icy world that's been floating far from the sun its whole life, has enough internal heat still to be driving this kind of convection that's erasing these craters and changing a very significant part of Pluto's surface. So I'll just leave you with this little take-home fact that you can share with your friends. Pluto has a giant frozen lake of toothpaste-like ice, which is just as cool and wacky as it sounds. Thank you.
Let's thank Sarah for her wonderful talk. Our next speaker is Professor Masha Barakta.
All right. Okay. All right, hello everyone. I will tell you about particles and black holes and how to look for particles with black holes. So let's start with particles. As we already heard, all of us and most of things in the universe that we understand are made up of electrons, neutrons, and protons. These are the fundamental ingredients that you and I that are all inside all of us. Zooming in a bit further on the neutron itself is not a fundamental particle, it's a composite particle which is made up of quarks and gluons all tangled up together. And we know many other types of particles which all have funny names, and I won't get to them today, but there is still more left to discover. And how do we know that there's more left to discover? Well, one way is by looking at what we already see and asking questions. One question is, how does physics look going forward and backward in time for different types of particles? So let's take our electrons and let's look at them moving around forward in time and then moving around backward in time. But did they move around backward in time, or are these just like different electrons going from right to left instead of from left to right? If you look at all possible experiments, you can't tell the difference. There's no way to distinguish the two. What about if we look at neutrons? Well, the same thing happens. Let's look at this neutron going forward in time, and the neutron going backward in time. There we go. Turns out for the remote to work, I have to point the photons at the computer. Good. So that's cool. So everything is working. Maybe this is a fundamental principle that all fundamental particles move the same forward and backward in time. But we actually know that this is not the case for quarks. We know their interactions are not the same forward and backward in time from looking at other experiments. So how do all of these quarks and gluons inside the neutron coordinate to make sure that the whole neutron goes the same forward and backward in time, where all the quarks are doing their own crazy stuff that's violating this, what's called time reversal symmetry? That's been a question for the last 50 years or so. And one solution was proposed by these folks here. So Petchin Quinn first proposed the idea of a new symmetry that then Weinberg and Wilczek extended to propose a new particle called the axion. And the axion talks to the quarks and the gluons and tells them that the whole energy of the system will be minimized if the whole neutron moves the same forward and backward in time. And just like you don't ask, oh, why is a ball sitting at the bottom of the hill? Well, it's sitting at the bottom of the hill because that's where its energy is minimized. If there's an axion, you don't ask, why is the neutron looking the same forward and backward in time? So that's the first point of my talk, is the axion tells neutrons to behave the same both going forwards and backwards in time. And since that's what we observe in our experiments, the neutron looks the same forward and backward in time to 1 part in 10 billion or so in our most precise experiments. And of course, we can't really run time backwards, but there's a precise sense in which we can do those experiments. So we're very interested in looking for this particle called the axion. changing gears, let's talk about black holes now. So remember this about the axion. So black holes are very cool objects going from the particle level, as in the first talks, to the astrophysical level, as in this previous talk. Now let's talk about big astronomical objects. So black holes are very cool. This is an image or a simulation of what the black hole in the center of our galaxy looks like. This is the light that's going around it. Why are black holes cool? Well, one is they have an escape velocity that's faster than the speed of light, and also they can turn around really fast. Why is that the case? Well, what's the escape velocity? Here we're all sitting here on the Earth. If I try to jump up, I fall back down because of gravity. How fast do I have to jump up to escape the Earth? It's about 11 kilometers a second, which is around 25,000 miles an hour. That's very fast. I'm not going to do that, but we can do that with rockets. It's possible. If I'm standing at the surface of the sun, I don't recommend it. It's very hot. But if you do, then it's even harder to jump up because the sun has more mass, so its gravitational potential is deeper. And then you have to jump up at about 600 kilometers per second, which is about 1 million miles an hour. But it's not just about the mass. It's about how close you are to the center of the object, because gravity gets weaker the further away you go. So if you take the sun and you collapse it to a more dense object, like a neutron star, which is what happens at the end of life of many a lot of stars, then you have to really try really hard to jump up off the surface of the neutron star. Probably you'll be a pancake, but you'd still be able to escape the surface of the neutron star if you go at about 20% of the speed of light. So light can escape, which is good. For black holes, the escape velocity is faster than the speed of light, and that's kind of what defines the black hole in the first place. Black holes are have such a strong gravitational pull that not even light can escape. But what else is cool about black holes? Well, they can rotate very fast. Why do black holes rotate very fast? And these are real black holes that we've seen out there in our galaxy, in our universe, and we've measured them, some of them, to rotate close to the speed of light. Well, if you have a black hole, if you have a star, it's rotating. Our sun is rotating, the Earth is rotating, right? And it's pretty big and fluffy. But then it collapses, and it goes into a very small compact object, which is the black hole. And now the black hole rotates very fast. I can't rotate that fast because I'll get very dizzy, but the black holes can rotate up to the speed of light because they're so compact. So why is the fact that black holes can rotate so fast and they have an escape velocity close to the speed of light, why does that make them exciting? Well, it turns out that makes them great particle detectors. That sounds really weird. But these black holes can actually be particle factories. So let me tell you about a process that can actually extract energy from a black hole, which is very counterintuitive because I just told you that black holes, not even light can escape, so it absorbs everything that hits its surface. But the black hole being a good absorber is actually great for what we want to do. Why is being an absorber great for what we want to do? Well, let's talk about friction. So if you have friction, that's a way of stealing away your energy, right? If I try to slide on this floor, I stop because of friction, so the friction takes away my kinetic energy. But imagine that I wasn't sliding on this floor, but I was sliding on like an airport moving walkway. And the moving walkway is going much faster than I'm walking, and I slide on it, then I'll actually get some extra forward kinetic energy or a forward velocity because the friction will actually grab on and push me forward. So if you have friction, but you have relative motion where the object is actually moving faster than you, you can extract its energy rather than it extracting your energy. Okay, So black holes are moving very fast, and they absorb very well. So can we extract their energy? The answer is yes. So this is a simulation where you have a black hole that is being shot at with some blue light, and it's re-emitting this very big red wave. So blue and red here are just telling you if the wave is incoming or outgoing, because otherwise it's hard to tell. You can see that it releases much more energy than what came in, and that came from spinning down the black hole. Now, combining this black hole effect with axions, it turns out axions act just exactly like those incoming and outgoing waves, but they have a small mass. So instead of flying off to infinity, they remain trapped close to the black hole. And the black hole, these axions keep extracting and extracting the black hole's energy until you have a huge number of these particles around the black hole. And that means that if we look out there and measure the properties of these black holes, if there are axions, they cause the black holes to spin more slowly. So you can use the properties of astrophysical black holes to look for these particles that were telling us that the neutron moves the same forward and backward in time. Thank you very much. And I wanted to say thank you for all the awesome collaborators that made this work really fun. So.
Hello, all right. Hi, everybody. I am Alana Pollack. I'm a professor at the Bothell campus of University of Washington. I'm going to talk about how do people even learn physics. We're going to get meta. All right. So I do physics education research. So that means that I look at how people teach and learn physics from the perspective of being a trained expert in physics. So we look at how do people learn, how do people teach, who's doing physics and why. Today, what I'm going to do, I'm going to try something a little bit different. I'm going to give you a crash course in what we've learned in PER so far, and you're going to get to experience some of it. All right, so we're going to think about 3 different perspectives we might take on how people learn physics. Maybe we think that learning physics is about knowing the principles of physics. Reasonable. Maybe we think learning physics is about learning how to problem solve and reason in the way that physicists do. And maybe we think that learning physics is about joining the community of practicing physicists. So we're going to take a look at each of these. And I'm going to tell you a little bit about what we've learned in PER, and we're going to see what it's like if we teach with those methods. Okay, so method 1, I'm just going to try to give you the physics, right? I have the physics, the students don't, we just got to give it to them. So here's some research we've seen with that. So has anybody here heard of the first force concept inventory or taken it in a class? Yeah, some people, okay. So these are tests that are designed to study students' understanding of Newtonian mechanics, and they've been designed specifically to get at common misconceptions. People have done a lot of research into what are the common ways that students will have confusions about these concepts, and they will write these tests to help support students in learning them and to also identify if students are learning these ideas or not when they take the class. So for example, here's a really classic problem, right? If you've got a moving vehicle and you throw something out of it, what does the trajectory of that thing look like? It's really tempting to give some intuitive answers here that aren't exactly right. And another thing you can do with these concept inventories is they make it easy to see a pre and a post. You give it to your students before, you give it to your students after they take the test, and you can see if they've learned some of these concepts. And on this forced concept inventory, this one about Newtonian mechanics, the questions are split into different themes. So you see we've got questions about kinematics, we've got questions about Newton's 3 laws, superposition forces. I think this is a pretty interesting result because you can see that it is really context dependent how much the students learned here, right? Look at Newton's second law, right? I would argue, as a person who teaches intro physics, if there's one thing I want my students to take away, it's probably Newton's second law. We're not making a lot of movement on that one. But superposition we're doing great on. All right, so if I were to teach from this perspective of, you know, my goal here is to give you the physics ideas, I might ask a question like this. So you are going to play my students for a moment here. All right, so we've got a satellite orbiting Earth at a constant speed, and I want to know what you can say about the satellite's acceleration. So go ahead and hold up however many numbers, however many fingers is your answer. Okay, and now chat with a neighbor. Chat with a neighbor about your answers. Maybe you agree, maybe you don't. What do you think? All right, in real life, I'd give you more time than this. All right, now that you've had a chance to talk to your neighbor, you get a second chance to vote. So let's see the fingers again. All right, I think I see more consistency this time. All right, so as it happens, it is towards the Earth because the Earth is exerting gravity on it. So, you know, what I want you to think about here is, what did you learn, right? If you were the student in this situation and you maybe didn't already know the answer, what do you think you would have gotten out of that experience? And also, what do you think I know, right? I'm here teaching you. I want you to learn that stuff. What do you think I gained by asking that question? Okay, maybe we want to take a different perspective, though. Maybe we think that we need to help students bridge the gap, right? We got to get from reading the problem to knowing the answer. All right, so people have studied this too. So there is another survey PER folks have developed called the CLAS. And what it does is it gives a number of belief statements to students, and they say how much they agree or disagree with those statements. And they're very subjective things, right? You can see some examples here. And the idea is that the folks who developed this survey gave the survey to lots and lots of professional physicists, lots and lots of students. So some of these answers are based on what professional physicists tend to say. Those are the examples on the left, and so those are termed expert-like. And some of them are the types of beliefs that we see much more often from students and not from professional physicists, and that's things more like on the right. Okay, so this is helpful because this survey lets us start understanding more about how students are thinking, right? Because when we say we want students to think like a physicist, one sense I might mean that in is problem solving, but I might also mean that in the sense of, you know, how do I as a physicist think about what physics is? And I probably want students to see it somewhat similarly. So people can use this survey to test that. Here's a cool, interesting but sad result. So this is showing, on the left we have a graph of the percent of students who had those expert-like beliefs about physics, and you can see we're centered around 70-ish. And after instruction, in the blue graph, you can see we are about the same, and in fact we've shifted down. And this is a universal pretty much result in physics, sadly. It is pretty common for students' beliefs about physics to become less expert-like over instruction. So this is something people are still studying and we're still working on. All right, but like I said, maybe what I mean by teaching students to think like a physicist is problem solving. So maybe people have studied how do students solve problems, right? So this problem, maybe you've done this. They want me to find velocity. I'm going to find a list of equations with v. I'm going to do them until I find one where I know all the other letters, and then I'm done. All right. Okay, so that's not ideal, perhaps. All right, if I were teaching with this idea of wanting you all to learn how to reason like physicists, maybe I would give a question like this. So now your task is you have to pick which sled here you're going to use to get down the hill fastest? Okay, so chat with a neighbor or two about this. What sled are you going to pick? All right, again, I'm going to cut this off way earlier than I normally would. Is anybody willing to share an answer? Could I get a brave person from the audience willing to say what they think? Which sled would you like to use? Yes? Can you say the Kraken? Why the Kraken? Coefficient of friction is smaller, and so that should mean it'll go faster, and the mass is bigger. Okay, nice. Other thoughts?
The avalanche,
Avalanche, okay.
because the force is equal to mu mg sine theta. And,
Ah,
and
Okay.
since it's got the largest product of mu and the mass, I think it'll reach the bottom first.
all right. Thank you, folks. All right. So, again, think about what was your experience of like for that, and what do you think my experience is like if I teach this way? All right. Finally, maybe we learn physics by joining a community of physicists. All right, so people who have studied this, they look at things like how do people develop a subjective sense of feeling like a physicist? These are some different things that they found correlate. This is from my personal research. I've looked at the effect that being a learning assistant, an undergraduate teaching assistant has, right? That's a way to pull young students into the community of physicists. And if I were going to teach this way, I might do something like this. I rub the balloon on the sweater, and it sticks to the wall. I need you to make an explanation with your neighbor. With your neighbor, can you come up with an explanation for why that just happened? All right. Again, I'm going to cut this super short. What I would normally do next is now you and your partner who have come up with a theory, I would then ask you to turn to another group and come to consensus. You would have to debate it together until you had a cohesive theory as one larger group. So I hope I've given you a couple other perspectives, but really, of course, this is how we learn physics. Thank you.
Okay, now it's time to let's welcome like all the speakers after this stage. It's time for questions. Before that, let's thank the 5 speakers again for their wonderful talks. Questions? Yes, please. Yeah.
Dr. Waters, right? Okay, so I just wanted to clarify that with your research with the 2D graphene, you're able to make superconductors without the necessity of cooling?
No.
Okay.
I avoided the notion. Okay, so what she's asking about is that superconductivity usually happens at really, really low temperatures. And kind of the exciting thing is, can we make superconductivity happen at room temperature in ambient conditions, no like tons of pressure equivalent to that of the center of the sun or anything? And the thing about twisted bilayer graphene is that the temperature you need to make it superconduct is even lower than all the others that we've ever come up with. But there is a little bit of hope because with these 2D materials, we have more control over them. We have more like ways to poke and prod these that we can think that hopefully we can like back out some solution. Now, is that going to come to fruition? I don't know, but there's still some cool physics that can happen along the way. Thank you.
While you're asking questions, please don't forget to scan the QR code and vote for your favorite talk tonight. I'll try my best. Oh, yeah, can you?
Yeah, Dason Waters.
Sarah Meridian.
Sarah Greenstreet.
Masha Baryaktar.
Alana Pollack.
Thank you for the wonderful talks. I have a question for Dr. Waters. How are you able to precisely stack the layers of nanomaterials?
Yeah, so we can come up with these like polymers that are good at sticking to the two-dimensional materials. And then what's cool is like 2D materials are really good at picking up other 2D materials. It's quite convenient actually. And then we can take that material, that polymer, if we design it like really cleverly, we can make it so that we can detach it and clean it off. So we pick them up with one polymer, keep doing it over and over, put it down, and then we have ways of like washing away that polymer, getting rid of it, so we're just left with that stack at the end, like the picture that I showed.
Thank you.
Yeah.
So
Hello.
let's do alternating this side.
This is for Professor Masha. I do not want to ruin your last name. This doesn't have to do completely with what you're talking about, but maybe please explain a little bit more about when you gain more energy than you give a black hole. Does that decrease the speed of the rotation of the black hole? And if so, does that cause the black hole to evaporate faster? Thank you.
Yeah, great question. Yes, exactly. So when you're taking away its energy and its rotational energy, and the rotation speed of the black hole does go down, and the rate of evaporation of the black hole is not going to change very much. It's going to be pretty similar for the two cases, and actually off the top of my head, I don't know which one is faster, but for astrophysical black holes, it's going to be many, many times longer than the age of the universe. So the black holes that will evaporate within a reasonable amount of time are roughly the size of Mount Everest rather than the mass of the sun.
Hi, it's for Dr. Bayaktar. The question comes in two parts. I wonder that because most black hole observation have been indirect and not through direct photography, how have we been able to measure its angular momentum? And second question is, have we ever actually observed the axion around the black hole, or is that a proposed experiment? Thanks.
Great questions. I was hoping someone would ask the first one because I didn't have time to get to it in my talk. So yes, so there are two ways that we can measure the rotation of the black hole, and you're right that we can't look directly at the black hole, so we have to make indirect measurements. One is we've seen black holes merging through their emission of gravitational waves in the LIGO Gravitational Wave Observatory, and as the black holes merge and form a new heavier black hole, that sends out ripples in the fabric of space and time. And the way that those waves are created depends on how fast the black holes are spinning. For example, and especially if their spins are not aligned with each other, they'll precess and they'll add some extra periodicity on top of the waves that you can measure. And so the gravitational wave observatories have already measured that some of the incoming black holes have very large spins. They've also seen ones that have spins consistent with zero. The other method is by looking at stuff falling in the black hole. For example, if the black hole has a star going around it, it's going to start stripping off the star and create an accretion disk of a bunch of hot gas around the black hole. And eventually, there's a point of no return of the gas where it starts to directly fall into the black hole, And that point depends on how fast the black hole is spinning, because it changes, it drags the space around it in a different way. And so by observing not the black hole itself, but the hot gas around it, you can tell how close it is to falling into the black hole, and from that infer the spin. And the second one is, no, we have not yet observed axions. Probably you would have heard if we've discovered a new particle. So, but keep an eye out because we're still looking for it. We're doing these measurements, and you know, any day with new gravitational wave observations, you could hear about discovery of axions around black holes. So.
Hi, I have a question for Dr. Sarah Greenstreet. So, you said that the global inner heating of Pluto is like a long-term thing, like since its like birth. So like, is there any indication from like other parts of Pluto that's indicating the global heating, like the inner heating?
Any other evidence that there is heating in Pluto's interior? Was that the question? Sorry, I just want to make sure I understand correctly.
So like just like on other parts of Pluto, just like elsewhere, like other than the nitrogen ice.
Yeah, it's really that part of Pluto's surface, which is, it covers something like at least 20% of that hemisphere of Pluto that was observed, is where that ice field is covering. And we see those convective cells over that entire part of the surface. And so that is really the only and the strongest evidence that we have that there is still this continual heat source that's still hot enough to actually be changing the surface of Pluto. So that's really the only evidence we have, but it's pretty powerful evidence that that is true.
So due to the time limit, let's do the last question.
This is also a Pluto question. So is any nitrogen ice seen deep in those craters up away from the heart region? And if so or if not, does that tell you anything about, say, a temperature difference between the heart region and the region up in the mountains?
Yeah, I'm not sure if I have a really good answer to that question. I think nitrogen ice is the most prevalent ice on Pluto. And so I think the answer is that it's very likely that there is still nitrogen ice in those craters as well. There's a lot of other ices in the highland region as well. But as far as whether there's a temperature difference, sorry. Yes, I'm not sure I have a really good answer to your question, is my answer.
Okay, thanks for all the good questions, and I know those talks are so wonderful. I also have a lot of questions written here, so I hope I can have a chance to ask them after that. So now let's see which one is the favorite talk. Now we have a winner. So the favorite talk goes to Dr. Sarah Greenstreet. And we have a second prize, goes to Dr. Jason Waters. Congratulations. Congratulations. And we have souvenirs for every speaker. Thank their fantastic talks tonight. And thanks for your attention tonight, and hope you enjoy, at least I enjoy this a lot.